Well, greetings out there in YouTube land. Rusty, Jack, and I are back with the third and final installment in the 1957 Fender Vibrolux video series. In this episode, we will actually go into the circuit, replace some parts, make some repairs, and discover some mistakes that were incorporated in the circuit and in the tube chart by Fender. At the end, there will be a sound test with my regular shop guitar and with a mystery guitar that I think you'll have no trouble identifying. If that sounds at all tolerable, then pull up a chair and be seated because the show's about to begin. Hey Jack, you going to take a second out from eating and help me with this video? Judging from the crunching, the answer is no. Well, thanks to the wonderful service from the fellows at Antique Electronics Supply in Tempe, Arizona, I ordered the parts on Thursday afternoon, and Saturday morning they were delivered. Here we have just an absolutely spectacular replacement speaker, P10R-F. F means it's a limited edition speaker that was made for Fender for some of their custom shop amps. And it has a much better, more Tweed-like tone than the standard P10R that Jensen offers. The regular P10R is said to be rather brittle, but this special edition speaker is said to have the warm Tweed tone right out of the box. I'm going to install this speaker so that the owner of the amp can use it for public performances without worrying about damaging the original speaker. And I will also recone the original speaker and include it so that he can install it back in the amp to restore it to originality anytime he wishes. I'm going to make a video on how I recone the speaker, so if you're interested about that, stay tuned, and that'll be a separate video following this series. I also received the 3 Sprague atom electrolytic capacitors in the original 16 microfarad capacitance value, but at a slightly elevated 475 volts DC. These capacitors cost about 5 times as much as the Chinese capacitors, but in an amp like this, it seemed to me like the best was the way to go. I also got a couple 1N4007 diodes. I'll only use one of them, but this is to replace that Selenium rectifier. You'll see how I do that in just a few minutes. These diodes are rated at 1000 volts and 1 amp capacity. Okay, I've made a pigtail for the new speaker out of a twisted black and white wire just like the original, and then an RCA plug on the end. Now it's time to replace the original electrolytic capacitors. As you can see, each of the positive leads has its own eyelet on the board, so what I'll do is heat the solder here until I can lift the leads straight out from these 3 eyelets, and then repeat that process back here with the negative leads. Okay, here's the positive leads released from the eyelet board. If you notice, there's a little bulge here and here on these first 2 caps. This one though, no bulge. So I think these, although they test okay and work okay now, it's probably best that these 2 are being replaced. Okay, the 3 Astron Mini-Mite electrolytic capacitors have been cleanly removed from the eyelet board, and now it's time to install the Sprague atom replacements. Just for fun, let's check the ESR values on these original Astron Mini-Mites. The first one that had a small bulge is 1.9. Second one with a small bulge, 1.5. And the one with no bulge, an amazing 0.92. First Sprague atom, 1.3. Second one, 1.3. And the third one, 1.4. Now the question arises, could these original filter caps have been left in place? And to be honest, I would say yes, if this amp were going to receive just limited use and wanted to be kept completely original as a collectible amp or maybe for resale. But such is not the case because the owner intends to use this for public performances, and for that reason more reliability is called for, so hence the replacement of the originals with the 3 Sprague atom caps. Now also, these will be kept very safely in a sealed bag, and the amp can be restored to normal by having these capacitors reinstalled back in it, and it would probably be virtually undetectable. And here are the 3 new Sprague atoms installed, and out of respect for Lupe, I put them in just as parallel and even and straight as I could. I'm sure she could have wired the whole amp in the time it took me to do this, but I really wanted it to look nice. Okay, the schematic says that the bias voltage should be minus 31 volts DC. Let's see what the bias voltage is using the Selenium rectifier. Okay, and the bias voltage with the Selenium rectifier in place is around minus 29.5 or 6 volts DC, which is what, about 1.5 volts below what the schematic recommends. Now, we discussed diodes in great depth in a recent video series on power supplies, and I hope that you recall from that the diode has polarity. Unfortunately, Fender labels it wrong. This end over here with the vertical minus sign is the cathode and should be minus, and the arrow is the anode, and that should be positive. The second bit of confusion here is the banded end of the diode should go toward the 10K resistor. The unbanded end should go toward the 56K resistor. Now comes the second bit of confusion, and that is, even though the tube chart says that this is a 5F11 circuit and a 5F11 schematic, the resistor in this position is 6,800 ohms, which is appropriate for the 5E11 chassis. But we're going to take that in stride, and in this 5E11/5F11 circuit that we're working on, we're going to put the banded end of the diode toward the 6,800 ohm resistor. Okay, as you can see, I've removed the Selenium rectifier from the circuit, and I've used jumpers to replace it with a diode with the banded end facing the 6,800 ohm resistor. Okay, I flipped on the power switch, and we see here that the bias voltage is much higher than it was with the Selenium rectifier. So this tells us 2 things. Number 1, diodes are a lot more efficient. And number 2, if you change your Selenium rectifier to diode rectification, you'd better rebias your output tubes. Otherwise, they're going to be operating at too cold of a bias level. Remember that the higher the bias voltage, the lower the plate current. Okay, now just for safety, I've wrapped the ends of the cut wires from the Selenium rectifier with masking tape so they can't touch anything and short out, and then I'm going to tuck them between the 2 layers of the eyelet board. So the Selenium rectifier is still present and appears to still be wired, although it's not, and in its place is this nearly invisible diode between these 2 eyelets on the board. Well, here is the biasing data with the diode instead of the Selenium rectifier. This is the resistance of the output transformer primary winding to the left tube and to the right tube, voltage drop across that resistance, plate current in milliamps, and plate dissipation in watts. This will be 7 watts and 7.3 watts. Now recall that in amp circuits that have fixed bias, that is that the cathodes are grounded, you want to bias at about 70% of maximum, which is 12 watts for a 6V6. So we want around 8 watts here for our plate dissipation. As you can see, these values are about 10% low, which would correspond to the 10% increase in bias voltage that we got when we switched from the Selenium rectifier to the diode. So now what I'm going to do is reduce this 56K resistor value just a little bit to let more of our bias voltage go to ground and lower it, and therefore increase our plate current about 10%. I did a little calculating, came up with 330,000 ohms, which in parallel with the 56,000 should give us a little bit higher plate current. Let's see. Now instead of the voltage drop of 7.6 volts, it's now about 8.4 volts. Let's see what type of PD value that yields. Now with that increase in voltage drop from 7.6 to 8.4, the plate current is up to 24.2 milliamps for a plate dissipation value of 8.06 watts, which is just about ideal. So here's the end result. The 56K original bias resistor is still in place, and I piggybacked a 330K resistor across it to give a parallel reduced resistance that gives us an ideal bias voltage and correct plate dissipation value for our 6V6s. And the left-hand 6V6, which was biased at 7.0 watts, is now up to about 7.6 thanks to the reduced bias voltage. Okay, here's a chart showing the final bias readings for the Fender Vibrolux amp. As an extra feature, I did them with and without the current limiter. So you can see that it does make a difference in your bias settings. I think it's silly to sit here and read the chart to you, so if you really care about these values, why don't you pause the video so that you can read them carefully. And if you don't, then let's just move on to our next topic. Okay, here's Jack lurking under some wicker furniture. Now, I'm going to throw his favorite toy, and you are not going to believe the kind of reaction that we get from him. Ready? I'm going to throw it. There it went. Jack, I just threw your toy. Now that I've been looking at this circuit for a while, I think I found a rather severe design flaw, and it has to do with the input jacks. If you plug into input number 3, you'll lift this leaf away from the contact, and your impedance to ground will be 68K in series with 68K in parallel, which should be around 100K ohms to ground. If you plug into jack number 2, you lift off here, your impedance to ground is 68K plus the two 68Ks in parallel for a total of 100K ohms to ground. But what happens when you plug into input number 1? You lift off here, there is no way to ground. Now you have no grid leak resistance, and it's going to change the bias of the tube and eventually either have the tube run away and start howling or shut down. Okay, let me give you an audible demonstration of this. I'm going to lift each of the leaves off of their grounds, and you'll be able to hear the hum caused by my finger touching the contact. As you can see, I mean, this really isn't an acceptable situation. And the first triode is not going to be able to function properly without any sort of ground reference for its biasing or any way for accumulated electrons to escape from the grid. My solution for this problem is to add a 100K resistor for the input jack number 1 leaf to ground. And the easiest way to do that is right here. This is the input from that leaf number 1, and this is ground with a 100K resistor in between. Now all 3 input jacks have the same impedance, and will provide about the same amount of volume. So there's no issues with unplugging from this one and plugging into this one and blowing the speaker out of the cabinet. And what else is strange is that this, I think, badly designed input circuit is not restricted to the Vibrolux. Look up the Deluxe, the Tremolux, all of those early Tweed amps, and you'll see they all have the same input scheme. And then one final touch, after talking it over with the owner, I thought it might be best to detach the so-called death capacitor from its connection up here on the fuse holder and leave it in the amp, but just lay it down with some shrink wrap over the wire lug coming out the end so that it can't touch anything. Now it's time to install that replacement speaker in the cabinet, and I use lock washers and I tighten the nuts finger tight. You don't need to torque them down with a 3-foot breaker bar to like 600 foot-pounds. You're going to end up warping the speaker basket. Okay, finger tight. And then to be sure that they don't unscrew, I'm going to take a little piece of plastic hose like this and push it down on the end of the protruding stud so that the nut cannot possibly come off. There you can see the little piece of hose is screwed down tight against the nut, and it's the best lock washer in the world and real easy to undo. You just unscrew it off the stud if you want to remove the nut. Now it's time to reinstall the chassis, and don't try to install it with the cabinet right side up and you're trying to hold it with one hand and then start those little nuts and washers over here on either side with the other hand, meanwhile sweating and shaking like a dog passing a peach pit. Okay, instead let gravity be your friend. Turn the cabinet upside down and just set the chassis down onto those two studs. Next, we flip the cabinet over on its face and install that lower panel. I'm going to leave the upper panel off for now because when I'm testing this, I want to be able to get at the components if I need to. Well, here we are back pretty well where we started, except for some improvements. Control panel looks like $1 million. New electrolytics and little minor changes that don't jump out at you. That really beautiful new Jensen speaker installed happily against the baffle board. New 3-wire cord down here ready to be plugged in. Tube chart. Okay, that's about it. Let's plug it in now and see how it sounds. Here's Jack reclining on the wicker coffee table. Let's see if he'll now go for his favorite paper toy. Ready, Jack? Here goes. Well, at least he looked at it. Okay, we've got the volume down around 2 because this beast is loud. The tone is at 5 out of 10. The tremolo is off. Let's start out with the bridge pickup. Now both pickups. Now the neck pickup. Let's see what kind of bass response we have. Okay, now it's time for the tremolo with both the depth and speed at 5 out of 10. Now let's try the tremolo with maximum depth and a speed at about 7. Okay, now maximum depth and speed. Now, just for fun, let's try a different guitar, see if you can figure out what it is. Here's the bridge pickup. Now this is the neck pickup. This is both pickups. Well, that's about it for this third and final installment in the Fender Vibrolux saga. We rooted around in the circuit and updated some of the components to provide reliability for the owner so that this amp can be used for public performances. I hope you enjoyed the video series and that you'll stay tuned because I'm going to be posting the how to recone a speaker video if and when I ever receive the reconing parts. So meanwhile, that's it for us. We appreciate the time you spend watching our videos and wish you the very best. So for Rusty, Jack, and me, it's adios and bye for now. Here's Jack checking out his portrait. What do you think? Looks just like you.